Have you ever wondered how to add up the inverse squares of all positive integers? This is the famous Basel problem. 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on. Today, we are going to evaluate this sum using a method often attributed to the physicist Richard Feynman, known as differentiation under the integral sign. First, we need to simplify our target. It turns out that if we can find the sum of the odd inverse squares, 1 over 1, 1 over 9, 1 over 25, we can easily find the total sum. The sum of the odd terms is exactly 3/4 of the total Basel sum. So let's hunt for that odd sum. We start by defining a specific integral that contains a parameter. Let's call it a. Consider the integral from 0 to pi over 2 of the arcsine of a times sine of x. If we set a to 1, the arcsine and sine cancel out, leaving just the integral of x. That evaluates easily to pi squared over 8. Keep that number in mind. Now we apply Feynman's technique. Instead of integrating directly, we differentiate the entire integral with respect to our parameter a. When we move the derivative inside the integral, the arcsine turns into an algebraic expression. We're left with the integral of sine x divided by the square root of 1 minus a squared sine squared x. Through a clever substitution, setting u equal to cosine x, this complicated integral collapses into something manageable. It evaluates to a clean, simple function, the arcsine of a divided by a times the square root of 1 minus a squared. Now we have an expression for the derivative of our integral, I prime of a. To get back to I of a, we integrate this result with respect to a. If you look closely at that derivative, you might recognize it. It is exactly the derivative of 1/2 times the arcsine of a squared. This gives us a powerful equality. Our original integral equals 1/2 times the arcsine of a squared. Here is where the magic happens. We expand the arcsine using its Taylor series. When we integrate that series term by term, we generate a sum of fractions. Specifically, we generate the sum of the odd inverse squares. By equating our two results, the geometric evaluation of pi squared over 8 and the series expansion, we prove that the sum of odd inverse squares is indeed pi squared over 8. Finally, we return to our first step. Since the odd sum is 3/4 of the total sum, we multiply pi squared over 8 by 4/3. The result? Pi squared over 6. If you enjoyed this explanation, hit subscribe and check out our other math videos.